So welcome everyone to the next IIT seminar. So today it is my great pleasure to welcome Troy Day, who is going to be talking to us about testing models of the distribution of fitness effects of mutations. Troy comes from Queen's University in Canada, and if you don't know his great book on Biologist's Guide to Mathematical Modeling, I highly recommend that you check it out. No, I'm not paid either by him or the publisher, but it is a great book. With that, please, Troy, the floor is yours.
Checks in the mail. Thanks for the invitation to give a talk here. I'm looking forward to this. I'm going to talk about some stuff here that is work that I did in collaboration with a postdoc that was in my group, Olivier Cotto, who's now with INRIA in France. And it's work that is focused on trying to understand the shape of the distribution of fitness effects of mutations, as the title suggests. And I'll explain exactly what that means in a little bit more detail as we go along here. Here's the outline of what I want to cover. Pretty simple. I'm going to tell you about what the problem is. I'll tell you about sort of the approach we took to analyze it mathematically, some of the mathematical results. And in the end, really what I want to do is show you an application to the data. And I guess maybe the sort of take-home message to me with this stuff is that what Olivier and I did here, I think, is a nice example of applying what ultimately are really some relatively standard results in certain areas of the mathematical literature to a problem in biology where they hadn't been applied before. And I think it gives, hopefully you'll see, it gives some useful insight into this interesting problem of the distribution of fitness effects. Before I start, though, what I want to do is talk about a different, simpler warm-up problem to kind of illustrate the problem, and hopefully you'll see exactly what the problem is from this example. So let's imagine we're interested in something like metabolic rate. So here's a distribution of metabolic rate of individuals standardized on some scale here. This is the number of individuals. And suppose the thing we're interested in is understanding why the shape of this distribution of metabolic rates is the way it appears in this empirical data set. And in particular, I want to consider how we might build a model to understand the evolution of this distribution of metabolic rates. And so one simple thing you might do is you might take a model where I'm going to suppose metabolic rate is made up of a bunch of independent are not necessarily independent, but the sum of a bunch of traits, x1 through xn. And there's coefficients here. I've just got a linear weighting of these different traits that go into making up metabolic rate. And let's suppose that each of these traits is subject to stabilizing selection in some way. And let's imagine that we're dealing with a very large population where there's no worry about demographic stochasticity or anything like that. And we'll imagine that when mutations occur, they're unbiased. So the only thing that's really happening is natural selection's favoring particular optimal values of each of these n traits. I'm going to simplify it a little bit more, and let's imagine that we're going to enforce some kind of symmetry to reduce the number of parameters, and I'm going to reduce it down to basically two effective parameters. One is the number of traits that are involved, and the other is an average optimal value of the trait. And then you could let this model go. You could try and analyze it. You could build a simulation, run the evolutionary dynamics on it. There are two parameters here that you get to choose when you're trying to fit this to data. And if you did that in a model like this, you can get a result that looks like that. So here's the model fit, the curve here, lying over top the data. And then the conclusion from that might be metabolic rate seems to be the result of the evolutionary optimization of a number of component traits that underlie it, because I've got a model here that fits the data very well. Now, I want to, and this might not work very well in an online format, but I'd like to stop here and ask if people are happy with a conclusion like this, or if they have any concerns about drawing a conclusion like that from a model as I've described it. I don't know if anybody's willing to voice an opinion. I know Aaron will be.
You know me pretty well. It seems like you've got a model, right, which is basically gonna produce a Gaussian distribution and it'll fit anything, right?
Exactly. Yeah, so that would be my worry too. I mean, there's a central limit theorem underlying this, right? And so it's somehow I've got a bell-shaped distribution of data. It's not all that surprising that I build a model that's the sum of a bunch of things and I end up with a model that fits that reasonably well. And it's that problem that I want to address in the slightly more complicated context. And so here's the context. what people typically do in this area is they're interested in the distribution of fitness effects. So what is that? This is data where people have taken E. coli in this case, and they've generated a bunch of mutations from a wild type genotype. And then they've measured the fitness of each of those mutations by competing it against some reference competitor and measuring the fitness as a growth rate in one way or another. Here it's a relative growth rate, the Malthusian growth rate over some standard. And they get a distribution that looks like the bars here. And the question people are interested in is, why does that distribution take that shape? Can we predict why it has this form? Because, I mean, that's important to know evolutionarily, because the influx of mutations determines a lot of important things in evolutionary biology. And so can we build a model to understand that shape? It's also interesting if you measure, not surprising, if you measure that fitness effect distribution in different environments, you get a different result. So on the right here are the same mutations measured in 8 other environments that are characterized by different antibiotics in this case. And you see very different shapes. And the question is, why did they have those shapes? And can we somehow build an evolutionary model to predict that distribution shape? So there are a variety of models, and I'll tell you a bit about the kinds of models people have built. And so all of them you can kind of think of as modeling in some way the mapping from genotype space to fitness. So on this plot, I've got frequency or probability density on the vertical axis and fitness on the horizontal axis. So these histograms are just different fitness bins, and I'm going to kind of focus on models like that. And so then there's a space of all possible genotypes. We take a wild type genotype and we generate a bunch of mutations. That's what's shown in red here. And you measure their fitness and they get mapped to one of these fitness bins. And so this distribution of fitness effects, which is this histogram, you can think of as arising from a particular genotype fitness or genotype phenotype map. The curve here is just a continuous probability density approximation of that histogram. And so all of the models people build, you can sort of think of as just specifying in some way or other this map from the space of genotypes to this histogram. And there are a few that people probably know quite well. The most well-known is Fisher's geometric model. But
Troy,
there,
can I ask a quick clarification question? So I get that conceptually there's a map from the set of genotypes, but don't you need something a little bit more? Don't you need to know something about how accessible all those genotypes are via mutations?
well, so that's a good question. I mean, the way these studies are done is you start with like this little one here I've labeled G wild type, and you generate a set of mutations. So those are sort of typically
I see.
one-step mutations from that
I
one.
see.
But you're right, there are probably a bunch of other uh, more
Okay,
distant mutations, and more than that, you won't see some because some are lethal. So all of these things are a little bit conditioned on only those non-lethal mutations as well,
okay,
because anything that's
okay,
truly lethal you wouldn't see.
got it.
So let me tell you how I'll just focus on 2 models. I'll spend most of my time talking about Fisher's geometric model. The way that model works is you take this space of genotypes and you embed it in what mathematically you'd call a metric space. So the idea is you take this space of genotypes, which doesn't really have any structure in it necessarily in an abstract sense, and you suppose every genotype can be mapped to a point in Rn. And the idea is that this Rn characterizes n different traits, phenotypic traits in some way. Then you specify there's a point in Rn, which is the optimal point to be in terms of all of these n different traits. And then you also specify some form of typically nearest neighbor mutation. And from there, you can then map what any one of these mutations is going to do in terms of its fitness effect. Because I do a nearest neighbor mutation in Rn, then that tells me what the fitness is because I have some kind of Gaussian, high dimensional Gaussian fitness function over that. And that tells me my fitness, and that maps me to the distribution of fitness effects. So there's a sense in which the model is kind of just specifying these things in some way, but that's how these models work. And you can imagine you get a different result depending on the environment you measure it in, because you may be closer or further from the optimal phenotype. But notice there's no statement of what these phenotypes are. They're just kind of abstract n-dimensional space here. The NK model is basically the same thing, but the metric space is now a sequence space instead. And the distance that's used is something like Hamming distance instead. So both of them are metric spaces. You have some space where you throw all your genotypes, you assume nearest neighbor mutation in some metric, and you overlay some kind of fitness function on that space, and that gives you your mapping. The thing that's kind of curious and interesting, and what got Olivia and I interested in this problem, is that if you look at these, and most of the models people look at are Fisher's model, they work incredibly well. I mean, remarkably well at explaining the distribution of fitness effects. And that got us to wondering about that problem I used in my introductory example. Is that because there's some sort of attracting distribution that naturally falls out? Or is it really a statement that what we're modeling here is an accurate representation of what's happening evolutionarily? And I'll just show you the data I showed you at the beginning of my talk. Let me get this right here. The blue curve in all of these plots is an approximation to Fisher's model, Fisher's geometric model. You end up with two parameters in the model, like I did in my pretend example. And when you fit those two parameters, that's what the blue curve is in all of these different plots here. So you can see it works, except for the cases where there's some bimodality, it works incredibly well. And then question is there some kind of null expectation? Is this a good indication that the model's right in some sense, or are these just kind of expected results because, like I said, there's some sort of central limit theorem kind of thing going on? So I want to tell you how we tried to analyze that, or how do we try to approach it. And I'll start with some simple examples. So let's imagine we have only two fitness values possible, a low fitness or high fitness. Every mutation has one of those fitness effects. And let's suppose there are only two mutations. So that means that there are three different possible DFEs, distribution of fitness effects. Both mutations could have low, one could have low, one could have high, or they could both have high. So there's three possible DFEs, but there are four possible mappings from genotype to fitness. There's only one mapping that places both genotypes in the low bin, and one that places both in the high bin, but there are two different maps that produce this distribution where one is low and one is high. Okay, and that's kind of the underlying idea of everything that I'm going to talk about, is how does that scale up as the number of genotypes gets large? Because we're typically talking about a high dimensional genotype space here and large numbers of mutations. So if you just increase to 4 mutations, still 2 fitness possibilities, you now have 5 possible DFEs. That's what's drawn across here, all the way from all 4 of them being low to all 4 of them being high. And you have 16 possible genotype fitness maps. So only one of them, again, puts everything in low, and only one puts everything in high. And you can see that now there's 6 that generate this even distribution and 4 that generate the other 2. And you can imagine as I increase the number of genotypes in the genotype space here, it looks like, of course, the number of DFEs gets large, but the number of mappings to DFEs grows in a way that's much faster than the number of DFEs themselves. And so you might wonder if somehow these DFEs are all concentrating on a particular kind, or sorry, these maps are all concentrating on a particular kind of DFE that's attracting in a sort of central limit theorem way. And then the idea would be, well, these maps are not necessarily equally likely, but maybe a sensible null model, and that's where I'll go later on, is to treat them as though they were equally likely and just pull one at random and ask, what kind of DFE do I get? And so the probability I get this DFE with the star here is just 4 over the total, 16, so it's a quarter, right? And so at least under that null model, the probability I end up with a DFE like this is 25%. How does that change in the limit as n gets large is going to be the interesting thing. But I want to be a little bit more, maybe subtle is not the right word, but a little bit more tied to the data or something like that than just pulling randomly. Because as I said, the environment you measure things in clearly makes a difference. If I measured out everything in a lousy environment, I'm going to get a different distribution than if I measure them in a good environment. And so I don't want to draw these maps randomly from the entire space of possible maps. I might want to focus on a subset of possible maps, depending on what environment I measure things in. So if I measure them in an environment that's a good match between the species and the environment, I might be in that subset. There's a medium match or a poor match where most of the mutations are then high fitness mutations. So I want to somehow focus attention only on a subset of all the possible maps. And if I do that, of course, I can do the same thing. In the case where I'm randomly choosing from that subset, I can ask, what's the null result of that? And the probability of pulling that one conditional on this subset is then 36%, right? And again, the question will be, how does that scale at large? So he's going to generalize things. Now I'm going to set it up in a M fitness bin. So I'm going to fitness values. There'll be N mutations, and I'm going to be interested in what happens as N gets big. The different possible fitness values, we'll just label A1 through AM. That's the values along this axis here. And then I'm going to define these random variables X sub I. There's going to be N of them, and those are going to be the fitnesses of a mutation I. And I'm going to think of those as IID random variables, all drawn from some distribution Q of A. Okay, and so when I specify that distribution, that's specifying a kind of model for how I'm imagining this distribution of fitness effects arises. And I'm going to define just capital X here to be the vector of all of these random variables for each of the different possible mutations of interest. And so one way to think of this is a realization of this random vector X corresponds to a randomly chosen genotype fitness map. As soon as I have a realization of that vector, that tells me where every single one of those N mutations gets mapped to on the horizontal axis here. And so that gives me a map. And that map will produce a distribution of fitness effects. And I'm going to denote that by P sub X here. So that's just the proportion of all of the mutations in that sample that end up in the first bin, all the way through to the proportion that end up in the M bin. So this is sort of the empirical distribution, if you like, from that particular realization of X. And as I said, different models of the DFE correspond to different choices of this distribution Q here.
I'm sorry to disturb.
Yeah, go ahead.
Are you assuming there's only one mutation, or are there many mutations?
There are N mutations, but I'm going to treat them all in their assignment of a fitness as an independent assignment.
But they all happen at the same time. So you determine the effect of many of N mutations happening.
Yeah.
Okay, thank you.
Well, sorry, but they're independent. I'm measuring each one only with a single. So I'm not allowing two mutations in the same individual. There's only ever one mutation in any individual that I'm measuring the fitness of. Okay, so I'm
not quite understand it, but go ahead.
Okay.
So this is sort of the marginal distribution of fitness effects without any epistasis or anything.
Without any epistasis, exactly. Okay, so that's the setup mathematically, and I'll just we'll go through some of the analysis. Most of this, if you know this area, it's tied to information theory. Most of these results are pretty standard, but I'll go through them in enough detail. Hopefully you can actually at least kind of see what's going on. So here's the first mathematical result that's going to be important, and then I'll explain how there'll be two mathematical results that are important, and I'm going to put them together to give me the thing I want. So the first result I want to do is I want to imagine choosing a random genotype fitness map, and I want to ask, what's the probability it produces a particular distribution of fitness effects? So if I go back for a second, if I can go back, I guess I don't know, I'm having trouble going back. But if I choose a realization of that X vector, then I'm going to get a distribution of fitness effects from that. And I want to know what is the probability of any particular distribution of fitness effects happening. And the answer to that is not too hard to compute. And I'm interested in the case with large N. Okay, so here in the middle of this thing is the probability I'm interested in, the probability that the empirical distribution of fitness effects is equal to any particular P I might be interested in. Then I'm logging that, and I'm taking the ratio, I'm dividing by N and looking at the large N limit. And when you compute that, you get something that converges to the yes, that's right. Negative, this is the Kolbeck-Leibler divergence between P and Q. So if you don't know what that is, I mean, this is the definition of it down here, but you can think of that as a measure. It's not a true distance, but you can think of it as a measure of the distance between the distribution Q and the distribution P. where really I'm talking about the product distribution Q here, where the distribution I get by applying Q independently n times, and I want to compute somehow how far away is that from the distribution P of interest. That's what this quantity tells me. And so what this means is if I just exponentiate both sides, the probability in the large N limit of getting any particular DFE is exponential in the distance between the distribution of interest and Q. And it's exponentially small. As N gets big, of course, there are many, many possible DFEs. And so any one of them is going to have a probability that gets very, very small as N gets big. But I can compute the asymptotic probability of any one of those of interest. So that's the first result that is going to be important. Because remember, what I'm going to do is draw a random one. And I want to know random one from a subset, actually. What's the likelihood of it being any particular distribution of interest? And so, as I said, I want to focus on a subset of distributions. So I don't want to consider drawing a random genotype fitness map from all possible maps. I want to restrict attention to some subset of maps because I'm imagining that the environment I measure things in will determine which of those subsets that I might want to be focusing on. And so I'm going to call that this capital pi, I guess it is here. That's going to be the subset of DFEs that I'm going to imagine I'm interested in. And so I want to then get my second result is going to be if I instead randomly choose a genotype fitness map, and I'm not asking what's the probability of a particular one happening, but rather I ask what's the probability that it falls within some subset pi. That's going to be a useful quantity that I'm going to put together with the first one to show you how things come, what I want. I can combine those two things together to get what I want. Okay, so here I'm asking if I draw randomly now, what's the probability it lies in this particular subset? All right, and that's the second result. It's sometimes known as Sanov's theorem. It's a result that looks pretty similar to what I showed you before. Here's that probability again. Now it's the probability this distribution lies in the subset of interest. And I've got this scaling limit here. Again, it's the distance between something that matters. And that something is P star. P star here is the distribution within that subset that minimizes the distance between all possible distributions in that subset and Q. And so this is the kind of curious and interesting thing about Sanov's distribution. If I randomly draw a map and I ask, what's the probability the resulting DFE lies in this subset? You might think I'd need to compute the probability of all the possibilities in that subset. And if they were independent, add them up, or if they were mutually exclusive, add them up. But it turns out there's one distribution within that subset that completely dominates that probability. And it's the distribution that's as close as possible within that subset to the distribution Q that I'm sampling from. So it doesn't matter what all the other things in pi are. It's just that one thing that completely dominates that probability. And that's interesting because now I can put those two pieces together. So the first result gives me a probability of choosing a particular one. And if I focus on this P star as my particular one, I get that quantity. And then the second result gives me the probability of lying within a subset. And I get the same thing. So when I put those together, it kind of suggests in a particular neighborhood way, which I won't spend time dwelling on. It suggests that the probability of pulling a particular DFE goes to 1 as n goes to infinity. And that particular DFE is the one that minimizes the distance within the subset of interest to this distribution Q. So that's a lot. Let me say this in words maybe to hopefully make it a little clearer. So I'm considering the case of a large genome size, so large numbers of mutations, and I'm going to suppose that I choose a map at random from the subset of interest that's determined by the environment that I'm measuring things in. And I'm choosing according to some model that's defined by this distribution Q. By this distribution Q. The resulting distribution of fitness effects that I get will almost certainly, meaning as probability will go to 1, it will almost certainly be this particular distribution P star that has the smallest distance of all distributions within that subset to Q. So in other words, a randomly chosen GFE map under this model Q will produce a particular DFE, and it's the one given by this formula here. And that's maybe a little bit surprising. As n gets big, I'm choosing from this massive space of possible DFE maps, and I choose according to randomly, I get a very particular one coming out the other end, and it's sort of like a central limit theorem result. Geometrically, it kind of looks like this. I have this space of all possible distributions in DFEs. I focus in on only a subset of those, and now I'm going to randomly choose from that subset, assuming that n gets large. And when n gets large, everything kind of concentrates on one particular DFE. There are lots of different genotype fitness maps that produce that DFE, and that's why everything kind of concentrates on that particular one. And it's the DFE given by this expression, the one that minimizes this KL distance from all possibilities in that subset to this distribution Q. So you could ask, what does that have to do with a null model now? And so here's where I'm going to return to that idea of choosing truly randomly. So let's suppose all genotype fitness maps were equally likely. That seems like the most null model you could make. And by that, I mean, when I'm assigning a fitness bin to a particular genotype, all bins are equally likely. Okay, so I'm going to use that as my null Q, and I'm going to ask, what distribution do I get when I use that as my null model? So in that case, this limiting distribution P star, which is the one that minimizes this KL distance kind of quantity, unsurprisingly, maybe, if you know this area, it simplifies to the distribution that maximizes the information entropy within that subset. So this is kind of a maximum entropy result in information theory. If I'm choosing completely randomly, I'm choosing a fitness map completely randomly, subject to producing a DFE that lies in a particular subset, it will almost certainly be the one that maximizes the entropy of all possibilities in that subset. Okay, so that's the result I'm going to use now to actually compare with data. Okay, so the result there is if I focus on a particular subset, I have a very specific distribution I'd expect to observe. And so the question is, how do I apply this to data now? So to do that, I'm going to have to choose a measure of fitness. What am I quantifying that axis by? And I need to choose an appropriate subset of all of the DFEs. Remember, I'm thinking of that as some way to characterize the environment that I'm measuring things in. Okay, and so there are many ways you could make these choices, and I'm going to make some specific ones here, motivated mostly by what people have done previously in testing these models. So the first thing I'm going to do is I'm going to assume that fitness is measured by a growth multiplier, which I'll call rho. So what you do is you take a mutation, you put it in a medium with a competitor, and you ask, what is its relative multiplication rate over some period of time? So you can think of that as a per generation multiplication factor, if you like. And so that's what I'm going to take as my measure of fitness. And it's going to turn out to matter, as you'll see. So it is this multiplication rate, and these are the possible values it can take. There's the minimum possible multiplication rate, A, and then there are these bins, A plus delta rho, all the way up to the biggest possible value it can take in terms of its multiplication rate. And then the set pi that I'm going to focus on, I'm going to define that set by defining the mean fitness. And the idea is if I measure things in a crappy environment, then the mean fitness of all the mutations should be higher than if I measure things in a good environment. Because if I measure them in a good environment, most mutations might be bad. It's trying to capture the idea on that very first slide, or one of the first slides I showed you, that the environment I measure things in changes. It will at very least move that distribution left to right as a result of being in a good versus a bad environment. And so I'm going to characterize the subset of DFEs of interest by their mean. In other words, I'm going to fix the mean, and I'm going to ask, if I choose a random genotype fitness map, subject to it having a particular mean, what is the distribution of fitness effects that I get? Okay. And you can compute that pretty easily, and it's this thing here, which is, again, if you know this area, it's not surprising. It's a exponential-ish distribution, but it's a discrete distribution here. Well, actually, this is the continuous approximation of that discrete distribution, I should say. This is a continuum approximation where I'm thinking of the bins as being relatively narrow. But it's bounded below and it's bounded above, and so it's not quite an exponential, it's a truncated exponential. People tend not to measure rho, or they do measure rho, but they tend to not use that as the thing they compare when testing models. Instead, they use the Malthusian growth rate, which is a log kind of transform of rho. And so that's what this is here. Here's the maximum entropy distribution. If I instead change the scale and I look on this other scale, which is a scale involving the Malthusian growth rate, I get this distribution. And this is a kind of truncated Gumpert's distribution. And then I can do other things to simplify it. Like if I suppose there's no upper bound, both of these distributions have an upper bound of the possible fitness values of mutations. But if I was very far from any sort of fitness optimum, you might think that you could kind of take the limit as the upper bound went off to infinity because the upper bound is far away. That just simplifies these expressions a little bit, and I get these two things in the bottom for the multiplicative growth factor and for the additive Malthusian growth factor. All of these things, I reduce them to two parameters, just like in Fisher's model, though. So in order to fit these to the data, I have 2 degrees of freedom, just like Fisher's model does. Okay, and so I'll just show you how things compare, and I'll finish up by explaining how I think there might be other ways that are better to try and test some of these models. So this is that same data I showed you with the E. coli data, mutations with 8 different antibiotic environments. As I said, the blue curves were the Fisher's approximation to the Fisher's model. The red curve is this Gompertz model. Again, also a 2-parameter model fit to the data. And you can see it fits the data, I would say, at least as well as the Fisher approximation function fits the data. So these are all maximum likelihood fits. So you can see that, at least in terms of its ability to describe these distributions, I mean, there's, again, a lot of flexibility here in that I have 2 parameters I can play with. It fits just as well as Fisher's model does, and it doesn't really have anything going on in it. It's a completely randomly chosen genotype fitness map, except for an enforcement of what the mean of this distribution is. Here's some other data I haven't shown you. This is just different organisms now: bacteriophage, tobacco virus, VSV, and some more E. coli and salmonella. And again, the same thing. The blue is the approximation from the Fisher model, and the red is this Gompertz model again. And all of these, of course, the data sets are smaller in most of these, so it's a little rougher to do this kind of comparison. And there are other ways you can look at it by looking at cumulative distributions and things like that that are a little bit more powerful to see discrepancies. But overall, again, this sort of null model fits the data, I would say, as well, equally well as the Fisher model does. And so again, I guess the take home to me from that is that these kinds of comparisons are, I wouldn't say meaningless, but they're pretty weak evidence that the underlying model, Fisher's model, is somehow capturing something that's fundamentally biologically important. You can also take Fisher's model and you can simulate data from Fisher's model. And then you can ask, how does a null model fit the simulated data from Fisher's model? And that's what this is. And these are just different, again, different environments here. So the blue curve, so Fisher's model, you can simulate and you get the exact results. That's the histograms. The blue curve is this approximation I keep mentioning. That's an approximation to Fisher's model. And then the red curve is this Gompertz curve again. And you can see that in some cases, like in panel A here, the Gompertz model looks like it fits the Fisher model even better than the approximation to the Fisher model does. And so this is, again, just to say that I'm now generating output from this particular model, and my null model matches it just as well again. So I think further reinforcing the idea that this kind of comparison, at least, is a pretty weak measure of how well the model's capturing something that's actually kind of mechanistically important in what's going on. But there are ways you can find distinctions in the predictions, and it's related, as I said, it matters what scale you measure things on. And so you might not think it would matter much if I measure things on a log scale or on a non-log scale, which is effectively what I'm comparing when I look at the growth factor versus the Malthusian growth rate. But it does make a difference. And so if I go back to the multiplicative fitness scale, so I don't look at the Malthusian growth rate, that's what these plots are showing now. So you can see that the blue here is Fisher's model, again, for the multiplicative growth rate now, and it fits, I mean, this is simulated data again, it fits that data quite well, but I have a lot of difficulty fitting the null model on this multiplicative growth factor scale to the data because it's an exponential, right? And so I can have an exponential that's decreasing and it fits reasonably well when the distribution is squished to the left. It can fit reasonably well when the distribution is squished far to the right because I have an upper bound, so it's kind of a mirrored exponential. But it cannot fit well when I have sort of intermediate distributions like this because it never produces an intermediate hump in the distribution on that scale. So that's one way you can try to start to distinguish these things is by examining these measures on different scales, both a Malthusian scale and a multiplicative scale potentially. But there's also maybe to my mind, maybe a more useful way. Well, there's two more useful things I think you could do than just that. One of them is you could try and make predictions about not just the distribution of fitness effects, but the distributions of other things. So as Aaron mentioned, there was no epistasis in what we're talking about in these previous plots. They're sort of marginal distributions. But in Fisher's model, I could use that model to make predictions about what epistasis would look like. And I could do that in a null model as well. I could, if it's a null model, then any two genotypes are just randomly chosen genotypes, but I could compute the epistasis under the null model and I could compute it under Fisher's model. And I could try and fit the model both to the epistasis and to the distribution of fitness effects. And once you start to do that, of course, you're trying to fit more things with the same 2 degrees of freedom in the parameters, and it becomes much less forgiving. And so that's what these plots at the bottom here are trying to do. They're trying to trying to fit both the distribution of fitness effects and the distribution of epistasis simultaneously. This light curve, I can't tell what color it is on your screen. That's the null model where I've fit it to the epistasis here. And this is the resulting distribution of fitness effects that you'd expect to see from that null model. So it doesn't do anywhere near as well when I start to try and explain more than one of these things. But maybe I'll finish by saying there's I think an even more useful way that could be employed to try and understand how well these models are actually explaining things biologically. The first two I already mentioned, use the raw fitness measures or different scales, examine multiple predictions simultaneously. But I think an even more powerful thing would be to compete models against one another in some way. I mean, in a sense, that's what I've kind of done here, although I've done it only visually. I've competed the Fisher model against the null model by just seeing how well they can describe these things. And I think that's probably a more promising way to try and get a better understanding of whether or not any of these models have something sort of fundamentally biologically important to say about what's generating these distributions of fitness effects. But I've gone on longer than I expected to already, so I want to stop there and leave time for any kind of questions or discussions. Thanks.
Thank you so much, Troy. So if you have questions, as usual, please raise your hand in the participant list and I will call on you. So any questions? While people are thinking, maybe I will ask a perhaps obvious follow-up on that is it possible that the distribution of mutations by the nature of how it works is not going to give us anything fundamentally more interesting than a maximum entropy result just mechanistically?
Yeah, that's a great question. I mean, that sort of was my feeling after this, was that maybe these distributions don't tell us anything other than what you'd get out of this sort of similar result that I had at the very beginning in my pretend example, where, I could build something and I get the right looking answer because of a central limit theorem. This is kind of the same thing. Maybe that is an attracting form of distribution that kind of means that there's not much that can be gained by looking at just these distributions alone. We have to look at something else in order to actually determine whether our models for them have something meaningful in them.
Exactly. Thanks so much. Aaron, please go ahead.
Thanks, Troy. That was really interesting. So maybe you can help me think this through. I was trying to work out sort of what the role of this. So at some point you make a comparison between a uniform distribution and the distribution of effects, and that leads then to the maximum entropy. I'm trying to imagine what the role of that, what would happen if I modified that assumption, if I replaced that uniform distribution with, say, another distribution, or uniform on a different scale, or something. And in some ways, this comes back. I think this is interrelated with the question you had about what scale you view the data on, but I can't quite think it through. Have you thought about this?
I have. I mean, that's a great question, and I maybe I have, but I'm not sure if it's quite the way you're talking about it. But I'll tell you what I have thought about. So this comes down to my uniform choice is the specification in that Q distribution. If I go back, it's my specification here that this distribution that I'm assigning each genotype to a particular fitness bin, and it's my assumption that all bins are equally likely. That's what gives me the uniform thing. I'm sort of thinking, seems like this must be true, but I'm not positive. Any model that people have explored for the distribution of fitness effects, like Fisher's model or any of these other models, seems like it should be representable by some choice of Q. And so that's what made me think of in your question. That's the sort of place I've gone with that. So in comparing uniform versus not uniform, I've sort of thought of it as the comparison between a null model and a model that maybe has more structure to it, has more reason
Right.
for something other than completely equally likely assignment to these different bins. Now maybe choosing a different measurement scale would also do that. But that's sort of how I've been thinking of it. And so I could choose a Q that's not uniform. Maybe Fisher's model I can represent by a particular choice of Q. And when I compute the KL distance from the minimum distance within this set to Q, maybe I get something that's kind of more or less the maximum entropy distribution, and that's why they match so well. That's sort of where I've been thinking about that. I haven't gone there yet with those calculations, but
Right.
I'm not sure if that quite gets at what you're asking, but
No, it definitely does. Yeah, I mean, I guess in some way, the question you're asking at the end is, how can you tell whether there's more information in this? There's more to say about this distribution than simply that it's about as random as you would expect given what you measure.
exactly.
And so, it seems to me that one way of getting at that would be to, I mean, you showed some examples, for example, that have bimodality in them, right?
Yeah.
And even though in the limit, as the number of mutations that you're examining goes to infinity, everything basically collapses around the distribution that's closest, or that I guess has the either the most or the least relative entropy to Q. For finite n, there might be some way of getting at the probability that you see something which deviates a bit. And then I'm imagining you could do a kind of a hypothesis test where you say, well, actually these wiggles are probably real, or probably not, or that we can't tell. I don't know. This is very vague thinking on my part.
Yeah, no, that might be true. I mean, certainly it seems like you could try and do that numerically, if nothing else. I mean, the results that you use to get these asymptotic properties are all bounds on what these probabilities are. And so I don't know how to get a precise, other than under just the truly null model, which is not hard to compute precise probabilities. I don't know how you would do it otherwise. I mean, maybe you can for some particular cases, but you could always do it numerically. That'd be interesting, though.
Interesting.
Yeah, Axel.
Sorry. Yes, thank you, Troy. If in the spirit of your methodology, can I compute from the distribution of fitness effects the distribution of fitness in a population if there is a constraint on the distribution of fitness in the population, given that the fitter ones will have more babies?
So I'm not quite sure what you mean. So I have a distribution of fitness effects of each of these mutations individually. So I have mutations where each individual has a single mutation, all these different possible single one-step mutations.
Yes.
If I took that collection of single-step mutation individuals, I mean, I could compute the population fitness. If I wanted the mean, it's just the mean of that distribution, but I don't think that's maybe what
And
you
then
meant.
I iterate until I reach
Oh,
some
I
steady
see.
state.
And so then see what happens in terms of the evolution of the
Exactly.
population.
Yes.
Yeah, you could do that, sure.
But is it kind of is it difficult in the framework of your theory, or is it just numerically possible?
Well, it would just be a different, I think, a calculation on top of that. But I guess, I mean, in these cases, these are all asexual, so it probably wouldn't be that difficult to do because you could imagine they all kind of reproduce more or less faithfully, except with mutations. As long as you only allow one-step mutations, they just land somewhere in this distribution that we've computed, and then you could ask what happens, yeah. And I guess at the end, I mean, it would be a mutation selection balance you'd end up with, where there's a flux of mutations into this distribution. Again, assuming there's only one-step mutations and pressure towards always being the highest one.
Okay, thank you.
Can I hop in on that topic? So it wouldn't a problem be that so there's nothing constraining how high fitnesses can grow in this case, right? There's no other constraints.
Yeah, well,
so wouldn't it just grow?
Well, the problem I'm thinking about is evolution of prudence, where you get the highest long-term fitness if you optimize your short-term fitness, if you respect some constraints on your short-term fitness. And I want to know the distribution of the population, of the prudent population.
So there are two questions. So in this, at least, I don't think there's any. So when something like prudence happens, where does that come from? You replicate in some maybe really fast rate now, and that ultimately costs you something down the road. Whereas if you had replicated less, or if there's some kind of spatial structure, maybe then
exactly.
the one that was more restrained would ultimately prevail. So there's not really anything in the way people quantify fitness in these experiments that accounts for any of those sorts of effects, I would say. So these are very phony fitness measurements in the sense that they're all done in a petri dish and you throw them in and you compute this exponential growth rate, basically. And what happens in the longer term, the one that has the highest fitness in this distribution might not even be the one, that wins out over the long term in the simple experiment, because this doesn't account for any sort of resource depletion or anything at that point. The question about wouldn't it just keep getting bigger and bigger? It would, unless you're so in these cases, I've, where is it here? No, sorry, let me go back here. I start under the assumption that there's a lower and an upper bound on the distribution of fitness effects, in which case it wouldn't go off forever, but it would be pushed up against the high end mediated by mutation. But in the case where there is no upper bound, then absolutely it would.
Thank you. Thanks. Yeah, Liz, please go ahead.
Hi. Perhaps it is trivial, but I am thinking about that under the condition where these fitness distributions are measured. If I understand well, the conditions are fixed, and there is a standard genotype with which, in a competition experiment, they determine the fitness measure. And so what is the mechanism that can produce bimodal distributions in such situations?
That's not a trivial question. That's a great question. So something like this one here.
Yeah. So it is. I just cannot imagine. So if
Yeah, I mean, I have no idea. I don't know. And I think, I mean, it's sort of like what Aaron was saying about patterns like this, which are you don't generate from any of these models. There's something very particular going on here. I have no idea what it is, but the
but
other interesting,
perhaps there can be different interactions between these genotypes. I mean that the mutated one and the standard one, and it depends on their actual behavior. So it is like a phenotypic plasticity, and this phenotypic plasticity, depending on the particular micro conditions that which cannot be controlled by the experimental may produce such a pattern. That comes to my mind.
yeah, I mean, that would be interesting. And I guess it would also, if that was true, it would suggest that if you measured these fitness effects a little later on, when the relative abundances of the different kinds are different, you would get a different answer. The other kind of, I think, super interesting thing about this is all of these plots, these are the very same mutations. They're just different environments. So there's something about the interaction between them,
And the
interacting with
environment,
the
yeah, of
environment that
course.
does that. And I think it's not at all
And
true why that is.
and because these are competition experiments, it means that there is a feedback with the environment, and this feedback actually is just missing from the approach how the whole thing is done. So this was an
Exactly.
ecology. Yeah, so this is an ecologist remark who believes in.
And it's a completely reasonable remark. That's exactly right.
Okay.
It's assuming unlimited growth in all of these things, and somehow all that's fixed. Yeah.
Yeah, and perhaps this should be also included somehow. Thank you very much. It was very
Yeah.
interesting
No, it's a
and
great
very didactic. So even I understood a lot.
Thanks.
Thank you.
Sorry, Troy, I think you said this and I forgot. So how many, what's N in these experiments?
Oh, in these experiments, I
Yeah.
think in the E. coli, it's around 1,000.
Okay, thanks. So in other words, we cannot explain away the bimodality because by N being
No,
small.
I don't
That's all
think
I
it's
wanted
some
to
kind of
know.
weird sampling thing. No.
Yeah,
And there's a hint of it in this one too, although that one you might wonder if it's just noise. But um, I mean, there may be something similar about these are two different antibiotics too. I don't know anything about what they are. Maybe there's something similar in their action too. I don't know.
fair enough.
Yeah, great questions.
Other questions? There are no other questions then. Thanks so much again, Troy, for the
Yeah, my
indeed
pleasure.
very pedagogical, very good and enjoyable talk. And thank you everybody else for coming. And we will be back in 2 weeks. So stay tuned and hope to see you then.
All right.
Bye,
Take
everyone.
care, everyone.